Okay, so this is kind of the ultimate manifestation of what happens in the X stays in the X, and what happens in the Y stays in the Y. So, as soon as that ball leaves the ramp, that split second, it is no longer in contact with the ramp. What forces are acting on the ball?
Gravity.
So, gravity is trying to pull it down. Anything else? That's it. There's nothing else, right? There is nothing else acting on it. So here's a common misconception. You all want to think inertia is a force. So let's say, for example, I'm going to take this tennis ball and Isaac Bruce. You ready? So I'm going to throw it to Isaac, right? As soon as it left my hand, was my hand still capable of exerting a force on the tennis ball?
No.
No. Okay? Can't. Be cool if I could, because then I can, like, you see football fans like they kick a field goal, and the fans are doing this because they're trying to like alter the path of the football as it's flying through the air. It's like, just stop it. Okay? All the physicists in the world are going, you don't understand inertia. You don't get it. It's good for you to try. It's not going to happen. So, as it flies through the air towards Isaac, the only force acting on it is gravity. Does it have inertia? Yes, that's what keeps it going forward, okay? But don't include or don't confuse inertia as a force, because it's not. Now, since that's the only force acting on it, what's the only acceleration that it has? Straight, which is always going to act which direction?
Down.
Straight down, okay? So even though the ball has a Vx to it, don't confuse that horizontal velocity as having a force. Now, did there have to be a force on it to create the Vx? Absolutely. But after it leaves your hand, or after it leaves the ramp, nothing else happening in the X direction. So, if you look at x equals 1/2 at squared plus v naught time. So let's talk about this equation. In the x direction, what's going to be your acceleration? Do not make this difficult. 0. Why? Why is there no acceleration in the x direction? Because there's no force. Okay? No force. Hey, F equals ma. Force is 0. Acceleration is 0. So this part of the equation drops out. It's not there. So basically, you're left with x equals v naught time. We're going to make this fancy because it's projectile motion, and we're going to write that as range equals vx time. Okay? So all of this is. So range equals vx time is a derivation of 1/2 at squared plus v naught time. But we just don't worry about the acceleration part of it because it's not accelerated. So vertically, is there acceleration? Absolutely. And that acceleration is always going to point straight down. So now, when you go to this equation, and I'm going to write it as y equals 1/2 gt squared plus vy naught time, when it rolls off the ramp, or if it's a lemming problem in general, what's the initial velocity going to be in the y direction? So all of this drops out. Okay, all of that goes to 0. So like, for example, you all solved for time, and you said, oh, time is the square root of 2y over g, which is just putting it in terms of your vertical distance and gravity. So what are the only two factors that determine how long something is in the air? How high it is and your acceleration due to gravity. Now, there's one key assumption that's made, and that's that your initial vertical velocity is 0. If your initial vertical velocity is not 0, you can't do this. Okay? But on a lemming problem, that's the main assumption that you're making. Okay? Now, when it lands, it's going to have a Vx, and it's going to have a Vy. Okay? It's going to have a Vx and a Vy. So, what I'm asking you to find on that resultant section is the hypotenuse, and then I want that angle right in there. So that should be about, right here, that should be about somewhere in the mid-70s, okay? Ish, all right? Don't worry about subtracting it from 360 and all that good stuff. Just give me that angle. Cool with that part of it, okay? Now, to get your vertical velocity, you could use v squared equals v naught squared plus 2ax. But again, what's your initial vertical velocity in the y direction? 0. So this just is the square root of 2ax. So what's the only thing that determines your final vertical velocity? Two things. Height and gravitational acceleration. Okay? But with this one, as your distance increases, your velocity increases, and as gravitational strength increases, your velocity increases. But with time, that calculation of time, because it's 2y over g, on that one, as your gravitational acceleration gets bigger, your time actually becomes less. Okay, so just be aware of that. On the graphs on 6 and 7, make sure that I clearly see which is which, okay? Which is the drop ball, which is the ball that is rolled off. So let me kind of give you this visual. So here's your ramp. One ball goes out like this, and at the exact same time, one falls straight down. So it's like I tried to show you yesterday with the marble that got launched and one that got dropped at the same time. Okay, try to show you that. So with this one, do not make number 6 difficult. Okay? On the one that's dropped, what's its horizontal velocity? 0. Okay? Don't make it difficult. Is it ever going to have a horizontal velocity? No, because it's just falling straight down. Is the one that's rolled, is that going to have a horizontal velocity? But is it going to change? No. It's not, because if you look up above, you should only have one acceleration, which is pointing straight down. So, on the next one, with the vertical. So here's, this is going to be important today, so I want to make sure everybody understands this. The gravity mafia only affects vertical motion. So if you could do like a snapshot and find this one when it's fallen a certain time, that would match up exactly with the one over there. When this one is here, that one's going to be over there. The fact, and this is the ultimate manifestation of what happens in the x stays in the x, what happens in the y stays in the y. So even though this has a Vx component to it, it doesn't affect anything in terms of how long it's in the air or what the vertical velocity is at a particular point. So if you could watch one fall and the other one go out like that, vertically they would look exactly symmetrical. You could not tell the difference between them in the vertical motion. The only difference is that one has a horizontal component to it. Okay. On the back side, on number 1, with that time, because if that's wrong, probably everything is going to be wrong. That should be a little bit less than 2 seconds. All right? A little bit less than 2 seconds. Make sure what I say, hey, if the horizontal velocity was doubled, how would each of the following change? And I tell you this, but I just want to reiterate it. Just don't say, oh, it increases or it decreases. Worse yet, it's different, okay? It changes. Flip out, okay? So if there is a mathematical change, you need to say by how much it changes. It doubles, it increases by the square root of pi, whatever, okay? Or you can just calculate it. If you just want to do smash mouth physics, you can just calculate it. I don't care. But do something to indicate that. Now, let's just say hypothetically on number 2, on the back side, your time is 0.5 seconds. let's just say. And let's say that's what you have as your answer. How many significant digits did I give you in all of the data that you have for number 2?
4.
At least 3, if not 4. Okay? If you just put 0.5 seconds, that technically only has one significant digit because there's a decimal place and you count to the right. If this is what you write down, somebody is going to look at that and go, man, you have a slacker of a physics teacher. Dude, he only gave you one significant digit in your data. You can only have one significant digit in your answer. That is a bold-faced lie. I gave you good data, okay? I gave you very good data with at least 3 significant digits. So how should that be written?
With at least 3 significant digits.
How about 0.500? Because if you put 0.5, that's wrong. Because you're not conveying the precision of the data that you had. Okay? I gave you good data. Don't roll me under the bus. Okay. Now, let's talk about number 4 with the cliff divers at Acapulco, which is really a thing. You can go to YouTube and video this. So here's the cliff, and it's like 41 meters tall, which is up there a ways. And then you've got the rocks protruding out here, which are 12 meters. So here's Joe Cliff Diver. And you're trying to figure out how fast this person has to be running to clear the rocks. And if you mess this up, you'll never do it again, because you're just not going to make it. Because you're going to be falling really, really fast because you're falling 41 meters. So, basically, you're going to do range equals Vx time. Which one is your range? The 41 meters or the 12 meters?
12.
There's your range. How are you going to find the time? Root 2 d over g. So your answer to number 4 should be around 4. Okay? Which is doable. Okay? Like, you go out here and run in the hallway, typical high school kids, if you're running pretty fast, will run between like 7 to 8 meters per second. Okay? So you got to be moving a decent clip, but it's certainly doable. Now, if you're a cliff diver and you do this calculation and you get like 11 meters per second, not happening. Okay? World-class sprinters run at about 10 meters per second. If you do this and you have to be going, I got to be moving at 11 meters per second,
Don't jump.
just say no. Okay? Just say no. Now, I apologize, and I didn't point this out, but it is on the bottom of the page. There are some questions out of the book that need to be done. So I want to talk about a couple of them. And this is what we're going to lead into today, which is projectile motion, where you have an X and Y component to it. But it's the same idea. So no matter what, whether I throw it straight up or it's a lemming problem or whatever, you always assume that your Vx is just going to be constant. So since your Vx is constant, what's your acceleration in the X direction?
0.
0, okay? There just isn't it, okay? So when it asked about, they're using this where it talks about like the velocity like this, that's the speed, that's the resultant of the X and Y values. So when you launch something up in the air, okay, like for example, I'm going to launch this, okay? Dominic, you ready? So I'm going to launch this, okay?
Touchdown.
So, nice catch. Throw it back. Oh,
Ah, drop it.
nobody even saw it. I already got my glasses on. Okay. So, as that ball was traveling through the air, it started with a vertical component and a horizontal component. As it went through the air, what happened to the horizontal component? Absolutely nothing. It stayed the same. So whatever Vx I gave it at the beginning is whatever Vx it had when it landed. But it did start with a Vy. So as it went up, what happened to the vertical component of the velocity? It became, did it ever go to 0? Where?
At the
Maximum.
point.
Why?
Because in order to change direction.
Beautiful. It had to change direction. So even though it was moving, the vertical velocity went to zero. Just like if I threw it straight up like that, at the highest point, it's going to stop and it's going to change direction. So at its highest point, here's what I want you to see. The only velocity that it has at its highest point is just horizontal. Okay? So as that goes through that air, highest point, it only has Vx. As it flies through the air, what happens to your vertical acceleration? Does it change? No. So up throughout the entire flight, your acceleration vectors are always pointing straight down. So what's the only time that your velocity vector and your acceleration vector are at 90-degree angles?
Maximum.
At its maximum height, okay? That's the only time. Will they ever be parallel? No. What's the only time your velocity and your acceleration vectors could be parallel?
So it's going straight.
Perfect wall that it rolls perfectly down.
Yeah, or I just throw it up in the air like this, okay? If all you have is vertical motion. So if I give it any kind of Vx, they'll never be parallel, but they can be at right angles to each other. But if I throw it straight up, they'll always be parallel, but never at 90-degree angles, okay? So kind of keep that visual. Any questions on that lab?
If we didn't do the textbook questions, can we do them and then turn this over in class?
Yeah, that's fine. You'll have time. Just take my book. God forbid you have your own book. Mr. Burkamp, I'm just gonna borrow yours. Is that cool? You don't need it, do you?
No, on the back.
Okay.
No.
Yeah.
Ava. Ava. Camera Ava. Pick a number between 20 and 60.
42.
42 degrees. Okay? So we're going to launch something at a 42-degree angle. Right side, Ava. Pick a number between 10 and 30.
13. 27.
Okay.
What?
Okay.
Sorry, that was my alarm. My bad. I put my phone in the hallway and told it to go off at exactly
118?
what? 1:16 p.m.
Really?
Yeah. My phone's over there in the hallway. Yeah. Continue with the lesson. God. That was crazy. Such disrespect. Wow.
You know from this distance, I could just take you out with this pencil. Okay? Gone.
At what velocity would you have to do it?
I can't tell you that.
Oh, okay.
If I did, I'd have to kill you. Okay. So either way, this isn't going to end well for you. All right. So here's what I want to find out. I'm going to launch this thing at 27 meters per second at an angle of 42 degrees. So this path is going to go something like this. True?
True.
Will it have a horizontal component to its velocity?
Yeah.
Yes. It's going to have some Vx. True? Is it also going to have a Vy? Yes. We're going to call that Vy naught, my initial vertical velocity. As it flies through the air with the greatest of ease, what's going to happen to my Vx value? Absolutely nothing. It's going to stay the exact same. So if I know my Vx at any point, I know my Vx at every point, okay? Because it's not going to change. So if I ever find my Vx at any point in the flight, I know it at every point in the flight, okay? So, same Vx, same Vx. What about my vertical velocity?
It's changing.
It's changing, because that's where I have my acceleration. So, let's do a little trig. Let's get triggy with it. So, I need to find my Vy. How can I find my Vy?
Trigonometry.
Let's get a little bit more specific.
Sine.
Inverse. Make a
Sine
triangle.
42 times 27.
Make a right triangle.
Oh, sine.
How about the sine of theta equaling Vy naught over the velocity itself?
Hey.
Yay, yay for trig. So somebody take the sine of 42 degrees, make sure you are not in radian mode, and multiply that by 27.0 meters per second.
Wait, what's in the bottom?
That's just Vx.
So it's just, why is it kind of, with little like,
Huh?
why is it used like this?
We sig figs, round eight.
That's the hypotenuse.
Is it sine theta Vy
And you can just do
naught?
a
Oh,
squared plus b squared.
that V is your overall launch velocity.
Okay.
Then you get velocity.
So what'd you get?
18.1.
18.1.
We don't know.
Okay? So my initial is 18.1 meters per second. So if sine got me Vy, what's going to get me Vx? So we're going to do the same thing. Take the cosine of 42 degrees times 27.0 meters per second, and what do you get?
20.1.
20.1 meters per second. Okay. Now, here's the deal on a problem like this. Listen to me very, 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 very carefully. As soon as you use that 27 meters per second to find the x and y components, that 27 meters per second is dead to you. Don't ever speak of it again, okay? It is dead to you,
Dear heavens.
okay? Goners. Do not ever use the 27 meters per second again. It's done, okay? It is not Vx, it is not Vy. You just use it as a gateway vector to find the x and y components. And then you discard it. Never use it again. Now, temporarily, I want you to all act like none of this exists, okay? You're getting ready for the velocity exam. And I'm going to throw a ball straight up at 18.1 meters per second. I want to find the time up, the time down, the time total, the max height, and how high it is at 1.20 seconds into the flight. Okay? You're getting ready for the acceleration test. Old school. What do you know?
Gravity, acceleration, gravity.
You know your acceleration due to gravity, which is going to point which direction?
Down.
Thank God we didn't stumble on that one. I don't know. Which, maybe up? I don't know. Oh. Okay. What else you got?
Initial velocity.
That's my initial velocity. What else you got?
Final velocity.
Final velocity at the top is going to be?
0.
Okay. Anything else? Now, let's talk about the time up. So my time up is going to be bigger or smaller than 1 second?
Bigger.
Why?
Because the initial velocity is greater than 9.8.
Beautiful, okay? Because remember, this quick refresher on acceleration, right? Quick refresher on acceleration. So when that sits here and you've got that initial velocity of 18.1 meters per second, which is going to slip down like this. So here's the bigger truth. What does the slope of that velocity time graph give you? Which in this case is, so if it started at exactly 9.8 meters per second, how long would it take to go to 0? It would take exactly 1 second. So since that initial velocity is bigger than 9.8, I know my time up has to be more than 1 second. okay? So don't be afraid to go old school and go, man, what's gonna happen? That's what's gonna happen. So, how can we determine the time up? Oh dear Lord.
V equals V naught plus AT.
V equals V naught plus AT. So I need to solve for time, so what am I gonna do?
Subtract everything.
V minus V naught over,
A equals T.
so I got 0 minus 18.1 meters per second divided by negative 9.8 meters per second squared. Through the miracle of modern math, I have two negative values, so I don't end up with negative time, which would be really weird. So what do you get?
1.85 seconds.
1 point what?
85 seconds.
1.85 seconds. Which seems reasonable, right? We said it was gonna be more than 1 second, okay? If you approximate acceleration due to gravity to be about 10, you take 1.8, or 18.1, you divide it by 10, you get about 1.8 seconds. Hey, we're pretty close, okay? Seems like a reasonable answer. So the time up is gonna be 1.85 seconds. Now, this is a huge if. If the flight is symmetrical. If the time up is 1.85, what's my time down gonna be? 1.85. Now, that's a huge if it is symmetrical. If it's not, like if I got this action going, I can't do that. But if it returns back to that same height, it's symmetrical. So my total time would be 3.70 seconds.
Yep.
Okay. Now, let's talk about max height. There's a whole bunch of different ways you can get max height. What's the one way you can find max height without time? That equation. So if I want to find max height and not use time, because it's like, did I screw up the time? Not sure. So I got v squared equals v naught squared plus 2ax. Old school, v squared minus v naught squared over 2a is going to equal x. 0 minus 18.1, don't forget to square that, divided by 2 times negative 9.8 meters per second squared. What do you get? $20-ish.
16.714.
So 16.7 meters. Okay? Decent height, right? Okay? This room is about 2.5 meters tall. So it's a decent height. Now, there's another way that you can find the maximum height. And this is going to have one advantage, and it's 1/2 AT squared plus V naught time. If you want to think of it, this is like a function equation because it gives you the height as a function of time, okay? So if you do this, and this is a great tool, you're going to need to be able to do this calculation. And you have 1/2, make sure that you use negative 9.8 meters per second squared. Now, if I'm trying to find the maximum height using this equation, this function equation, what value of time am I going to put in? 0, 1.85, or 3.70? 1.85, why? That's at the time when it's at its maximum height, right? If I put in any other value, I won't get my maximum height. So, I'm going to have 1.85 seconds squared plus, now, here's a common mistake that's made. You see V naught, okay? Now this is going to go back to the initial problem where it was launched at an angle. When you see that V naught value, this is the manifestation of what happens in the x stays in the x, and what happens in the y stays in the y, okay? Do not put in that 27 meters per second. It's only the vertical component of the velocity that is affected by gravity. The gravity mafia can't deal with the x direction. It can only deal with the vertical direction. So when you do this, make sure that you only put in the initial vertical component of that velocity. So you got 18.1 and 1.85, you're still gonna get the same answer. Now, an interesting thing would happen. What if you put in 3.70 seconds in for time? What would you get? What'd you say? Zero. Why? Because that's when it's returned back to that reference point. So if you put in the total time, you're just gonna get zero. Okay? So if you want to find out the height at, say, 1.20 seconds, the only way you can do this is to use this function equation and put in 1.20 seconds. So now we found the maximum height, 16.7. Now I want to find out how far it's going to go. Now we're back to the actual projectile motion. Okay? Now I want to know how far it's going to go. What am I going to use? I'm going to use the total time. Why?
It's the whole flight together.
Yeah, it's the whole thing, right? It's going to be in the air for that entire time. So my time is going to be 3.70 seconds. And my Vx is going to be whatever that Vx was, to Vx or not to Vx. Vx was 20.1. So somebody take 20.1 meters per second times 3.70.
74, 37.
So 74.4 meters. That's a decent shot. It's not the entire length of a football field, but it's pretty close. Okay? So this would be a pretty good launch. All right? Now, huh?
What did we just launch? The squirrel?
I don't know, freshman. Okay. Now, here's where we're going to morph these two ideas together. Okay? You're going to shoot one squirrel, since you guys wanted an object. So, you're going to shoot one squirrel at an angle of whatever that was. 42 degrees at 27 meters per second. Okay? So 42 degrees, 27.0 meters per second. Now, at that exact same time, you're going to launch another squirrel straight up at 18.1 meters per second. Okay, so have this visual. One squirrel is going to get launched like this, going up, coming down, landing 74 meters away. Another one is going to just get launched straight up at 18.1. Which one will reach the maximum height first?
Same time.
Or is it the same time? Same time, why? But this one's moving at 27.
Because vector x doesn't have to do anything with the vertical acceleration.
Because what's the only thing that's affected by gravity? The vertical component of that velocity. Okay, that's the only thing that's affected by gravity. So here's what I want you to see. Imagine this. Okay? So, this one's going to go up like this. This one's just going to go straight up. If you could draw a line across here, they would both be at the same point at the exact same time vertically. When this one reaches its maximum height, that would reach its maximum height. The only difference is that this has a horizontal component to it. They're both going to have a vertical velocity of 0 at the top. The only difference is that this is going to have a Vx to it, which is going to keep it moving. So, in terms of the gravity mafia is going, you have a Vx? Don't care. Can't touch them, okay? Because it's Vx. We only operate in the vertical domain. So, the fact that it has a Vx and the overall launch velocity is 27 meters per second, gravity mafia goes, don't care. I got to stay in my lane. And my lane is the vertical. And conveniently, there's no horizontal mafia to mess with. Okay? So, let's talk about this. So the total range was 74.4 meters. I want to know how high it is when it's traveled a horizontal distance of 20 meters.
Oh, yes.
Or
Do divided by velocity.
R equals Vx time, right? So if I use R equals Vx time, I know my Vx, the range is 20 meters. I can figure out how long it took to get there. True?
Yeah.
So if I take 20 meters and divide that by, what was my Vx, 20.1? Ooh, that was handy. So that's basically gonna be about 1 second, right? 1 and some change. So once you get the time to calculate that height, there's only one way you can do this, and one way only. And that's if you go into that x equals 1/2 at squared plus v naught time. You take that 1 second, you plug that in for the time, and again, here's the most common mistake that's made. The most common mistake made is that you take that 27 meters per second and you try and put that in for v naught. Bad. Why? What's the only component that's affected by gravity?
The vertical component.
The vertical component. Okay, that's the only thing that is affected by gravity. So that's the only thing that goes in there. Okay, got it? Good? Grand? Okay. All right. Okay, so let me explain some of these questions. So question number 1, here's the tennis ball. I'm going to throw this to Isaac, okay? Situation number 1, I'm going to throw it horizontally with a certain velocity, right? Now, throw it back. Situation number 2, I'm going to throw it, but now I'm going to throw it faster, okay? Now, is the range the same?
Yes.
Yes. Is the Vx the same?
No.
Absolutely not. As Vx got bigger, what happened to the amount of time it was in the air? Became smaller, right? If it's in the air longer, the gravity mafia has more time to act on it. Keep that in mind when you answer question number 1. So you have 2 strikes that are thrown. One situation, the Vx is bigger than the other one. They're both going to get caught by the catcher, just like it demonstrated with Isaac. Look at it in terms of how long it's in the air. Okay? Now, when you get to number 2, listen to me, listen to me, listen to me. This is the magic frictionless Teflon puck. The puck is already moving, okay? It's already moving. You don't have to push it, okay? Don't push it. It's already moving, and it's frictionless. So the first thing that you want to do, and you know the mass, you want to draw the forces acting on the puck, right? So what are the forces acting on the puck? Gravity is normal. Now, this needs to be drawn to scale. It's 0.1 kilogram mass, it's 0.98 newtons, so that 1 centimeter equal newton, something like that. Okay, don't make it complicated. You're gonna draw the forces while they're up there on the table, and then you're gonna draw them as it's falling. Now, notice I put a couple of asterisks there on this one. It has not hit the ground. But you could just like slide a piece of paper underneath there, okay? There's just like the thinnest of margins, but it hasn't hit the ground yet, okay? Which gets weird if you think about it. It's a quick little thought experiment in terms of what it means to actually like touch something. So let's say with 24 seconds left in the room, Isaac starts walking towards the door. And at 12 seconds, I turn the light off, okay? Then he's gonna walk a little bit closer. At 6 seconds, I turn the light back off. At 3 seconds, I turn it back on, and he's walking closer and closer to the door, okay? So every half of a time, I flip the switch on and off, okay? So is the light on or off when he gets to the door? Or does he never get to the door?
He doesn't get to the door.
I never get to the door. 'Cause I'm
You never
too
get to
slow.
the door. Begins with a P. No. No, it begins with an X. Something's paradox. Xenox paradox? Xeno's paradox? Yeah, you get closer and closer and closer. So the point being is that you're never gonna get to the door, you're sucking it up. So we don't know if the light's on or off. Anyway, so here's the point of this story. It hasn't hit 0. Now, the next one, you're gonna draw acceleration vectors. Is it possible that it just doesn't have any acceleration? Yeah. Because if the force vectors add up to 0, what's your acceleration vector gonna be? So it's very possible that you don't have an acceleration vector, okay? When you get to C, you're gonna draw velocity vectors, and you're gonna have 2 sets of velocity vectors, one in the X and one in the Y. So if you're not sure if their velocity vectors are gonna change, look at your acceleration vectors. If you don't have a horizontal acceleration vector, guess what? What is your horizontal velocity not gonna do? Change. If you have a horizontal acceleration vector, then it is gonna change. So I want you to understand that the first one has fallen 0.6 meters, about like yay. The second one's fallen like 1.2. You want to draw the X and Y velocities at every point along that path.
Wait, which one's 1.2?
The second one. Okay, when you get to number 5 on the back side. So here's this golf ball, it's launched, and the angle is 30 degrees at 32.0 meters per second. You're gonna find the time, height, range. What's the first thing you're gonna do with the 32 meters per second and that angle? Find your Vy and your, are you ever gonna speak of the 32 again? No. It's dead to you, okay? It's a gateway vector. Just use it to get to the other ones. Now, when you get to number 6, you're still launching it at 32 meters per second, but now it's a 60-degree angle. So what's going to happen to your Vy relative to the 30-degree one? Is my Vy at the 60 going to be bigger or smaller than my Vy at the 30? Bigger. So you know your Vy has to be bigger. Okay? When you get to number 8, let me give you the visual on number 8. Here's this cliff. And the cliff is 20 meters tall, you're gonna hit a golf ball and it's gonna go like this. And it's launched at 40.0 meters per second with 3 significant digits, thank you very much, at an angle of 60.0 degrees. So there's a whole bunch of things that you need to find. So this is kind of old school projectile motion, okay, excuse me, old school accelerated motion. So what's going to determine your maximum height, your Vx or your Vy? Vy, and only your Vy. So this is like the ball off the building problem. Remember that big problem on the test? Okay, similar type idea. Now, when it lands, this is what's going to be different than the ball off the building problem. When it lands, it's going to have a Vx component and it's going to have a Vy component. Now, here's what I want you to think through before you even start to do the math. How is the Vx here when it lands going to compare to the Vx when it's launched? It's the exact same, okay? So you don't have to recalculate the Vx. But this ball goes up and then it falls all the way down to the ground. Is the Vy here, when it lands, bigger or smaller than the Vy that it's launched at?
Bigger.
Bigger. So because it's not symmetrical, you just can't take that Vy up there and make that the Vy here. You have to recalculate that Vy because it's not symmetrical. When you get to the questions and problems out of the book is horrible at significant digits. So when you get to problem 72, when you do your calculations, assume, even though there isn't, but assume that there's 3 significant digits. It'll make sense when you get to that problem. Okay? All right, I'm done. You're on your own.